You know that feeling when you're searching for something really specific online, maybe something brand new or super niche, and the results you get back are just, well, not quite right.
Yeah, it's like the search engine just hasn't seen enough examples of what you're actually looking for. It doesn't quite get it yet.
Exactly. So today we're diving into a really fascinating approach to tackle that exact problem. How do you build search systems that understand what you want, even if they haven't got tons of labeled training data?
hmm This whole area is called zero-shot dense retrieval.
Zero-shot dense retrieval.
Right.
And it's a tough nut to crack.
It really is. It's a fundamental challenge because, well, traditionally for search engines to learn what's relevant, you need to show them countless examples, pairs of questions and good answers, relevance labels.
Like training a dog, you need repetition. Show it what good looks like over and over.
Precisely. But what happens when you have a brand new trick, a new
Yeah.
kind of query,
hmm
and absolutely no examples?
Yeah.
That's the puzzle.
Okay. And that's the puzzle that a team of researchers tackled.
Yeah, exactly.
Yeah.
Lu Gao, Shuiguang Ma, Jimmy Lin, and Jamie Callan, they're from Carnegie Mellon University. And the University of Waterloo came up with a really clever idea.
Okay, so this idea aims to kind of sidestep needing all that labeled data. What's it called?
They call it hypothetical document embeddings, or HIDE for short.
High DE. Okay, sounds intriguing. Can you give us the quick overview? How does it work, high level?
Absolutely. So HIDE basically has two main steps. First, you put in your search query, right?
Mhm.
And HIE uses a powerful language model. Think of something like Instruct GPT, one of these AI models that follows instructions really well,
Okay.
to actually generate a hypothetical document, an imagined answer.
Ah, hypothetical. So not necessarily a real existing document.
Exactly. And here's the really interesting part. This document it generates, it might not even be 100% factually correct. But that's not the main goal. The
Yep.
goal is to capture the essence, the sort of linguistic shape of what a relevant answer would look like.
So it's like asking a super smart assistant to sketch out what a good answer might sound like, even if they don't have all the facts memorized.
That's a perfect way to put it. It's a
Yeah.
linguistic sketch. Then comes step two.
Okay.
It takes this imagined answer, this sketch, and encodes it into a dense vector, a string of numbers, basically.
Right.
And it uses an unsupervised encoder for this, something like Retrieval.
Unsupervised,
Yeah.
meaning that part didn't need query answer labels either.
Correct. That encoder, Retrieval, has already learned how documents relate to each other just by reading tons of text.
Yeah.
It understands document similarity without needing specific query answer pairings.
Ah, okay, I think I'm getting it. So step two is like the reality check. The language model makes this potentially slightly flawed sketch, but the encoder, which knows what real documents look like, takes that sketch and finds its place on the map of real information. It figures out what real documents that sketch is most like.
Spot on. It grounds the hypothetical idea in the space of actual documents.
Right.
And the way the encoder works, this dense bottleneck they talk about, it kind of squeezes the information down.
Right.
And in doing that, it tends to filter out the inaccuracies, the fuzzy details in the generated document, while holding on to the core relevance information. The stuff that the language model got right about the style and topic of a good answer.
So it's like saying, okay, the exact numbers might be off, but the kind of answer this feels like, that feels a lot like these real documents over here.
Precisely. So our mission today in this deep dive is to really unpack how HIDE pulls this off. We want to see how effective it actually is compared to other search methods, the ones that use labels and the ones that don't.
Explore what it means for the future, right? Especially when finding good training data is just hard.
Exactly. We'll look at results across different kinds of search tasks, web search, Q&A, even different languages.
Okay, great. Let's maybe zoom back in on that initial problem first. The challenge of zero-shot dense retrieval. You mentioned traditional approaches use query and document encoders. How do they usually work, and why is not having labels such a roadblock?
Right. So in the standard dense retrieval setup, you typically have two neural networks. One network looks at your search query and turns it into a numerical vector.
Okay.
And the other network does the same thing for every single document in your collection, also turns them into vectors.
Right, so everything gets represented as numbers in this vector space.
Exactly. And the whole goal of training these networks is to make it so that the vector for a query is really close mathematically to the vectors of the documents that are actually relevant to it.
And far away from irrelevant ones.
Precisely. They often use the inner product, sometimes called dot product, to measure this closeness. It's like equation 1 in a lot of these papers. A higher score means the vectors are more aligned, suggesting higher relevance.
Okay, so it's about building this shared map where related things are grouped together in the vector space. Makes sense.
hmm But to train those encoders to build an accurate map, you need a ton of labeled data, those confirmed query document pairs.
Like MS Marco, that huge data set.
Exactly. Datasets like MS Marco, with millions of human-checked examples, have been absolutely crucial for driving progress in supervised dense retrieval.
But as the researchers argue, you can't always rely on having a massive data set like that. Sometimes there are restrictions, or for new topics or really specific areas, that data just doesn't exist yet.
That's the core problem. Maybe you're building a search for internal company documents or scientific papers in a brand new field. Creating high-quality labeled datasets is just. It's often too expensive, too time-consuming, or sometimes literally impossible because of privacy or just the novelty of the domain.
It's like trying to find the best coffee shop in a town that just popped up yesterday. No reviews yet.
Perfect analogy. So zero-shot learning tries to solve the retrieval problem without needing any task-specific relevance labels. It's a bit different from transfer learning, where you might start with a generally trained model, but still fine-tune it on some task data. Heidi aims to work well right out of the box. No fine-tuning needed for the retrieval part.
Okay, that makes the Heidi approach sound even more valuable.
Yeah.
Let's get into its core innovation then, those two key parts. The instruction-following language model and the unsupervised contrastive encoder. Tell us more about the language model's role first.
Right, the first piece is that instruction-following language model, or InstructLM. These are the big LLMs like GPT-3 or similar models that have been specifically trained not just on text, but on following commands given in natural language.
So you don't just give it the query, you give it an instruction too.
Exactly. You give it the user's query plus a specific instruction. The one they used a lot of the paper was simply write a paragraph that answers the question. And the model then uses all its learned knowledge about language and the world to generate a document, a paragraph, that it thinks fits that instruction. A hypothetical answer.
And again, the key is it doesn't have to be perfectly accurate factually.
That's the crucial insight. It's not about factual perfection. It's about capturing the relevance patterns. What kind of language is used? What topics are covered? How detailed is it? Things you'd expect in a real relevant answer.
The paper had examples, didn't it, in Figure 1?
It did. Really good ones. Like if the query is, how long does it take to remove wisdom tooth?
Right.
The InstructGPT model might generate something like, it usually takes between 30 minutes and 2 hours to remove wisdom tooth.
Which sounds like a plausible answer, even if the exact time varies.
Exactly. It captures the shape of a good answer.
Yeah.
They also showed it in Korean. Query,
Yeah.
Hegia, Kegiagia, Egyo, Kira, meaning when did humans use fire? The generated text starts. Records of humans using fire appear from about 8 million years ago, and goes on about Homo erectus 1.42 million years ago. Again, it's generating a text that feels like a direct relevant answer in that language.
That's really clever. So the language model acts like a relevance blueprint generator. Now, how does the second part, the unsupervised contrastive encoder, the encon, use this blueprint to find real documents?
Okay, so this encoder they use, Contriever for English and Contriever for multilingual stuff, has been pre-trained on just massive amounts of text, but using a contrastive method. Meaning it learned to create vector embeddings where documents with similar meanings are close together in the vector space and dissimilar ones are far apart. And crucially, it learned this without seeing query document relevance pairs. It just learned about document similarity.
So it already has its own internal map of how documents relate to each other, based purely on their content.
Exactly. So you feed it to this hypothetical document from the language model. The encoder looks at it and says, okay, based on everything I know about real documents, where does this piece of text fit on my map? It embeds it based on its semantic similarity to all the documents it saw during pre-training.
And you mentioned that dense bottleneck thing again. How does that help here?
Right, because the encoder has to compress the hypothetical document's information into this relatively compact vector. Any weird details or factual errors that don't really match common patterns in real text, they tend to get smoothed out or lost in that compression.
So the noise gets filtered.
Yeah, it filters the noise, but it keeps the core semantic meaning, the gist, that is relevant to the query because the language model captured that relevance pattern.
Okay. And then the final step for retrieval. You take the vector of the hypothetical document and compare that vector to the vectors of all the real documents in your collection, using that inner product similarity measure.
That's exactly it. The real documents whose pre-computed vectors are closest to the hypothetical document's vector are the ones you retrieve as search results.
Wow. So you never directly compare the query vector to the document vectors?
Nope, it's indirect. You compare the imagined answers vector to the real document vectors. It's quite an elegant conceptual shift.
And the HID system itself, it doesn't need any training for this specific retrieval task.
Correct. It's purely leveraging the pre-existing, pre-trained capabilities. The language model was trained to follow instructions. The encoder was trained to understand document similarity, but HID itself just combines them. No task-specific fine-tuning needed for retrieval.
That sounds incredibly useful, especially like you said, when you're starting fresh with a search system or in a niche area with no labeled data. So the big question, how did it actually perform? What did the experiments show?
They really put it through its paces. On standard web search tasks, using the Tirashek deep learning tracks from 2019 and 2020, which are actually built on top of MS Marco data, HID significantly beat the baseline unsupervised contriever. That's maybe expected. But interestingly, it also consistently outperformed BM25.
The traditional keyword-based method.
Yeah, a very strong baseline. And what's maybe most impressive is that HID's performance was often competitive with models like DPR, ANCE, and even Contriever FT models that were specifically fine-tuned on that huge MS Marco dataset.
So a zero-shot method holding its own against fully supervised ones.
In many cases, yes. They showed solid gains in metrics like MAP and NDCG at 10. And its recall, finding relevant documents, was often right up there with the supervised models. That's a huge result for a zero-shot approach.
That really is remarkable. What about those situations where labeled data is truly scarce, the low-resource tasks?
They tested it on 6 different data sets from the BOKR benchmark. These cover things like scientific claim verification, SciFac, finding relevant arguments, Arguana, searching COVID research papers, track COVID. Really diverse stuff. And again, they saw similar big improvements over the baseline contriever. In many of these cases, HID was performing better than, or at least comparably to, the fine-tuned models like ANCE and DPR.
Any exceptions?
Well, on Trek COVID, the old-school BM25 actually edged out HID slightly, though HID still crushed the base contriever. And on a couple of others, like Fikie Finance and DBpedia, Encyclopedia Facts, the fine-tuned models did have a noticeable advantage.
Any reason why?
The researchers suggest that maybe those specific tasks could benefit more from carefully crafted task-specific instructions for the language model rather than the generic write-a-paragraph prompt. But overall, the picture was very positive for HID in low-resource settings. Like on SciFac, the boost in NDCG at 10 and recall over 100 was really substantial.
Okay, so it works well in English in low-resource settings. What about crossing language barriers, multilingual search?
Yeah, this is another really interesting test. They used the Mr. Tidy benchmark, which has languages like Swahili, Korean, Japanese, Bengali. Quite diverse.
How did HID do there? Did they need a specific HID for each language?
No, they used the multilingual version of the encoder, mcontriever, and presumably a multilingual instruction following model, and HID managed to improve upon the base mcontriever performance. It also did better than some other multilingual models that weren't based on contriever.
But how did it compare to a fine-tuned multilingual model?
There was still a gap. mcontriever FT, which was fine-tuned on multilingual MS Marco data, generally performed better than HID.
Okay, so not quite closing the gap with supervised methods there.
Not entirely. But the fact that HID showed clear improvements over the zero-shot baseline in these very different languages without any language-specific tuning for the HID process itself is still pretty impressive. They saw gains in MRR at 100 for several languages.
And why the remaining gap, do they think?
They hypothesize it might be down to the pre-training data. Maybe those non-English languages just weren't represented as extensively in the original training of the language model or the mcontriever encoder compared to English. Makes sense?
Yeah, that seems plausible. It's still impressive it generalizes as well as it does. Did they look at using different underlying language models for HID? Does the imagination engine matter?
They did. Besides the Instruct GPT model, based on GPT-3, they tried a big 52 billion parameter Cohere model and an 11 billion parameter FLAN T5 model.
Never bakery mean better.
Generally, yes. The trend was pretty clear. The larger, more capable language models tended to produce better hypothetical documents, which in turn led to better retrieval performance for HID. The NDCG at 10 scores consistently went up with the bigger models. So yeah, a better imagination engine helps.
Interesting. They also did a slightly weird experiment, right? Using HID with an encoder that was already fine-tuned, Contriever FT.
Yeah, that wasn't the main point of HID, obviously, since HID is for zero-shot scenarios. But they were curious about the interaction.
What did they find? Did Heidi mess up the fine-tuned encoder?
Not necessarily. It was a bit mixed. Using a weaker instruction model could sometimes slightly hurt the fine-tuned retriever's performance. But interestingly, using a really strong instruction model, like InstructGPT, could actually boost the performance of the already fine-tuned Retriever FT even further on one of the web search datasets.
Huh. So even a fine-tuned model might miss some nuances that the generative model picks up.
That's the implication. It suggests the generative approach might capture certain subtle relevance aspects that even supervised training on query document pairs doesn't fully instill in the encoder. Maybe potential for combining these ideas in the future.
Okay, let's try and pull this all together then. What are the big takeaways here? It really feels like Heidi offers a fundamentally different way of thinking about relevance.
I think that's the core insight, yeah. The big takeaway is that Heidi proves you can effectively model relevance through language generation by creating a plausible instance of what you're looking for, rather than just trying to directly score the similarity between a query and existing documents.
And that bypasses the need for those explicit relevance labels for the retrieval system itself.
Exactly. Which leads to those deeper questions you mentioned earlier, the ones the researchers raise in their conclusion.
Right, like, is numerical relevance just a kind of statistical shadow of true language understanding?
If you truly understand the language of the query and the language of potential answers, maybe that's enough. Maybe the ability to generate a relevant hypothetical document is the ultimate understanding of relevance.
And they push it further, don't they? Asking if, as these NLU and NLG models get better and better, could they eventually make traditional retrievers less central?
They do pose that question. Could we reach a point where generating the answer or generating a perfect query reformulation becomes the primary method, with retrieval just playing a supporting role? It's definitely a thought-provoking possibility for the long term.
It absolutely is. But thinking more practically in the here and now, what's the immediate value proposition of Heidi? Where does it fit?
I think its immediate value is huge, especially when you're just starting out. Launching a new search feature, dealing with a specialized domain, anywhere you don't have existing user logs or labeled data. Heidi gives you a way to get surprisingly strong performance, often near supervised levels, right from day one. That's incredibly useful.
And they suggested a hybrid approach, too.
Yeah, a very pragmatic idea. Use Heidi perhaps for the long-tail queries, the unusual, rare, or brand new ones where your supervised model might lack data and struggle. Meanwhile, let a standard supervised retriever, trained on the search logs you do accumulate over time, handle the more common head queries. Kind of the best of both worlds.
That makes a lot of sense. Okay, so bringing this deep dive toward a close, Heidi really seems like a genuinely innovative, compelling direction for zero-shot retrieval.
Definitely. It's this clever combination, the generative power of instruction-following LLMs, plus the semantic understanding of unsupervised encoders. It achieves impressive results without needing those direct relevance labels.
It's like teaching the dog the trick just by showing it a really good drawing or animation of the trick, and it somehow figures it out.
Yeah, something like that. It really shows the power we can unlock by creatively combining these amazing pre-trained models we now have. And its ability to generalize across tasks and languages without specific fine-tuning is a huge plus, especially where resources are tight.
Absolutely. And it leaves us with some fascinating food for thought about what relevance is and where information retrieval might be heading. This idea of modeling relevance through generation, it feels like it opens up so many doors.
For sure. You can imagine applying similar ideas to more complex tasks, right? Multi-hop QA, where you need to combine information. Or maybe making conversational search feel much more natural. Lots of exciting possibilities ahead.
Definitely something to keep an eye on. Well, thanks for walking us through that. It was a really fascinating exploration.
My pleasure. It's a really neat piece of work.
Until our next deep dive, everyone, keep exploring those ideas.